Welcome. Tonight, we're going to slow down and explore one of the most ancient and quiet travelers in the universe: comets. Long before telescopes, before science had names for orbits and gravity, comets were already moving through the darkness of space. They appeared without warning, glowing softly in the night sky, then faded again into the distance. For thousands of years, humans watched them in silence, wondering where they came from and where they were going. In this video, we'll gently follow comets on their long journeys through the solar system. We'll talk about what they are made of, how they form, and how some of them have been returning to the inner solar system for millions, even billions of years. We'll move slowly, taking our time, letting each idea settle before drifting to the next. This is a quiet exploration of space, guided by curiosity, soft explanations, and a steady pace. You can listen closely, or simply let the sound of the narration blend with the background as you relax. So get comfortable, lower the lights, and let your thoughts slow down. As we begin our journey with comets, the silent wanderers of the solar system. When we talk about comets, it's easy to picture only what appears in the sky: a glowing head, a pale tail, something beautiful and temporary. But beneath that soft light is a physical object, solid and ancient, shaped by conditions that existed long before planets formed. At the heart of every comet is the nucleus. This nucleus is the true body of the comet, and it is surprisingly small. Most comet nuclei are only a few kilometers across. Some are larger, some smaller, but none are anywhere near the size suggested by the vast tails they produce. In shape, they are irregular, often compared to rough potatoes or jagged rocks, rather than smooth spheres. The surface of a comet's nucleus is extremely dark. In fact, comet nuclei are among the darkest objects in the solar system, reflecting very little sunlight. This darkness comes from a coating of carbon-rich material, left behind as ice slowly evaporates over repeated visits near the sun. Beneath that surface, however, lies a mixture frozen almost perfectly in time. The classic description of a comet as a dirty snowball is not wrong, but it is incomplete. The ice inside a comet is not just frozen water. It includes frozen carbon dioxide, carbon monoxide, methane, ammonia, and traces of more complex organic molecules. Mixed throughout this ice are tiny grains of silicate rock and dust, along with carbon-based compounds that formed in the earliest stages of the solar system. These materials condensed more than 4.5 billion years ago, when the sun was still forming and the solar system was little more than a swirling disk of gas and dust. While planets melted, differentiated, and changed, comets remained mostly untouched, locked in deep cold, far from the sun. In this sense, comets are among the most primitive objects we can observe. For most of their existence, comets are completely inactive. Far beyond the orbit of the outer planets, temperatures are so low that nothing happens. Ice remains frozen solid. Gas does not escape. Dust stays locked in place. A comet in this state would be almost impossible to detect from Earth. It is silent, dark, and inert. A comet only becomes a comet in the familiar sense when it approaches the inner solar system. As the comet moves closer to the sun, sunlight begins to warm its surface, but instead of melting into liquid water, the ice undergoes sublimation. This means it turns directly from solid into gas. The escaping gas flows outward from the nucleus, carrying dust particles with it. Slowly, an atmosphere forms around the nucleus, thin, diffuse, and glowing faintly in reflected sunlight. This atmosphere is called the coma. The coma can grow incredibly large. While the nucleus might be only a few kilometers wide, the coma can expand to tens or hundreds of thousands of kilometers. In some cases, it becomes larger than the planet Jupiter. Yet despite its size, the coma is almost empty. It is far more vacuum than air, spread thin across a vast region of space. As gas and dust continue to stream outward, they interact with sunlight and the solar wind. This interaction gives rise to one of the most distinctive features of a comet, its tails. Most comets develop two primary tails, and sometimes more. The dust tail is made of small solid particles released from the nucleus. These particles are pushed outward by the pressure of sunlight. Because they retain some of the comet's original motion, the dust tail often curves gently, forming a broad, soft arc that traces the comet's path through space. The gas or ion tail behaves very differently. When gas molecules escape the nucleus, they can become electrically charged by ultraviolet radiation from the sun. These charged particles are then carried away by the solar wind, which flows directly outward from the sun in all directions. As a result, the ion tail points straight away from the sun at all times. This is why a comet's tail does not trail behind it like smoke behind a moving object. Even when a comet is moving away from the sun, its tail still points outward, away from the solar wind source. This detail puzzled observers for centuries and eventually helped scientists understand the role of solar radiation and charged particles in shaping comet behavior. As a comet continues its approach, activity increases. Jets of gas erupt from weak points on the surface, often from cracks or pits where sunlight penetrates more deeply. These jets can act like tiny thrusters, altering the comet's rotation. Some comets spin faster, others wobble or tumble unpredictably. These jets also shape the comet's surface. Over time, they carve cliffs, pits, and layered terrain into the nucleus. Images from spacecraft have revealed landscapes that look surprisingly rugged, with steep walls, smooth plains, and fractured crusts. Comets are not smooth snowballs drifting gently through space. They are dynamic, eroding worlds. Not all comets survive close encounters with the sun. Some approach too closely and are torn apart by heat and tidal forces. Others fragment slowly, shedding pieces with each pass until nothing remains but a cloud of debris. Occasionally, a comet breaks apart dramatically, its fragments spreading out along its orbit and fading from view. Each close pass near the sun strips away some of the comet's original material. Over many orbits, a comet can lose most of its volatile ices. When this happens, it may become inactive, no longer producing a coma or tail. At that point, it may resemble an asteroid, dark, rocky, and silent, even though it began its life as a comet. This blurring of categories is one reason comets are so important to study. They sit at the boundary between different types of small bodies, linking icy outer regions to the rocky inner solar system. Some meteor showers observed on Earth are caused by debris left behind by comets, scattered along their orbits over thousands of years. What makes comets especially valuable is not just their motion or appearance, but their chemistry. The organic compounds found in comets raise important questions about the origins of life. Some scientists believe that comets may have delivered water and organic molecules to the early Earth, contributing to the conditions that allowed life to emerge. By studying the gases released from comets, scientists can analyze their composition directly. Each comet carries a slightly different chemical signature, reflecting the region of the solar system in which it formed. In this way, comets act as messengers from different zones of the early solar nebula. When a comet lights up the sky, it is not just a visual event. It is a physical process unfolding in real time. Ice turning to gas, dust lifting into space, sunlight shaping invisible forces into visible form. It is a brief awakening of an object that has slept in darkness for billions of years. And once the comet moves away from the sun again, the activity fades, the coma collapses, the tails disappear. What remains is the nucleus, returning to cold and silence, carrying with it the memory of another close encounter with light. This quiet cycle, darkness awakening and darkness again, is what defines a comet's existence. And it is this cycle that continues to draw these ancient objects back toward the inner solar system again and again across immense spans of time. To understand comets fully, it's not enough to observe them when they briefly appear near the sun. Their true story begins far away, in regions so distant and cold that sunlight becomes little more than a weak presence. These outer reaches of the solar system are where comets spend almost all of their existence, waiting in darkness for spans of time that stretch far beyond human history. The first clues about the origin of comets emerged when astronomers began to carefully calculate their orbits. As observations improved, a clear pattern appeared. Some comets returned again and again, following predictable paths that brought them back within decades or centuries. Others appeared once, moving on extremely long, stretched out trajectories, never to be seen again. This difference suggested that comets did not all come from the same place. Short-period comets, generally defined as those that complete an orbit in less than about 200 years, tend to travel in the same general plane as the planets. Their paths are relatively compact, looping repeatedly through the inner solar system. These comets often become familiar objects, observed across multiple generations. Long-period comets behave very differently. Their orbits can last thousands, tens of thousands, or even millions of years. They approach the sun from every direction, above, below, and even opposite the direction in which the planets move. Some travel on paths so elongated that they spend nearly all their time in the deep outer regions of the solar system, barely bound to the sun at all. To explain this behavior, astronomers proposed two vast source regions. The first is the Kuiper Belt. This region lies beyond the orbit of Neptune and forms a wide, flattened disk encircling the solar system. It contains countless icy bodies left over from planet formation, objects that never merged into a full-sized planet. Some are small, only a few kilometers across. Others, like Pluto, are large enough to be considered dwarf planets. In the Kuiper Belt, conditions are stable and cold. Ice remains frozen and objects change very slowly. Many short-period comets are thought to originate here. A gentle gravitational disturbance, often caused by Neptune, can slowly alter an object's orbit. Over long periods, these small changes can push an icy body inward, where it becomes an active comet for the first time. Once a Kuiper Belt object begins interacting more closely with the giant planets, its orbit can shrink further. Some are captured into relatively stable paths that bring them back toward the sun again and again. These are the comets that become regular visitors to the inner solar system. Far beyond the Kuiper belt lies an even more distant and mysterious region, the Oort cloud. Unlike the Kuiper belt, the Oort cloud is not thought to be a disk. Instead, it likely forms a vast spherical shell surrounding the solar system, extending tens of thousands of astronomical units into space. At these distances, the sun's gravitational influence is extremely weak, and objects drift slowly along enormous orbits. The Oort cloud may contain trillions of icy bodies. These objects are believed to have formed closer to the sun early in the solar system's history, before being scattered outward by gravitational encounters with the newly formed giant planets. Over time, they settled into distant, loosely bound orbits, where they have remained almost unchanged ever since. A long-period comet begins its visible life when something disturbs this delicate balance. A passing star, the slow tidal pull of the Milky Way, or a dense molecular cloud drifting nearby can slightly alter an Oort cloud object's orbit. Even a tiny change can be enough to send it falling inward toward the sun. This inward journey is unimaginably long. For millions of years, the comet accelerates gradually, moving from deep darkness into regions where sunlight begins to have meaning. By the time it becomes visible from Earth, most of its journey is already complete. These first-time visitors are often the most dramatic. Because their surfaces have never been heated before, they retain large amounts of volatile ice. When they approach the sun, they can erupt with activity, producing enormous comas and spectacular tails. Many of the brightest comets in recorded history are believed to have come from the Oort cloud. But these encounters are dangerous. Some long-period comets are torn apart by heat and gravitational stress during their first passage. Others are flung out of the solar system entirely, their orbits reshaped by close encounters with Jupiter or Saturn. A few survive and are captured into shorter repeating orbits, transforming from rare visitors into returning comets. Although the Oort cloud has never been directly observed, its existence explains the distribution of comet orbits so well that it remains one of the most widely accepted structures in planetary science. Without it, the behavior of long-period comets would be nearly impossible to explain. Together, the Kuiper belt and the Oort cloud act as vast reservoirs of ancient material. They preserve fragments of the early solar system in deep freeze, far from the processes that reshaped planets and moons. Every comet that enters the inner solar system is a release from this frozen archive. Planetary gravity plays a critical role in shaping these journeys. Jupiter, in particular, exerts enormous influence. Its gravity can redirect comets, capture them, or eject them entirely. In this way, Jupiter acts both as a shield and a sculptor, controlling the flow of comets into the inner solar system. The paths comets follow tell a deeper story about the solar system's past. Their distribution suggests that the giant planets did not always occupy their current positions. Instead, they likely migrated during the solar system's early history, scattering icy material outward and shaping the distant reservoirs we observe today. When a comet appears in the night sky, glowing softly before fading away, it represents the final chapter of a journey that began unimaginably far from Earth. It has crossed from deep time into human awareness, carrying with it frozen material from the outermost edges of our cosmic neighborhood. And when it departs, whether returning to darkness or leaving the solar system forever, it leaves behind only dust, memory, and the quiet reminder that the solar system is far larger, older, and more dynamic than it first appears. When a comet enters the inner solar system, it does not drift aimlessly or choose its direction by chance. Its motion is governed by gravity, following paths that are mathematically precise, yet shaped by countless interactions over immense spans of time. These paths, known as orbits, determine how often a comet returns, how close it approaches the Sun, how fast it moves, and how long it remains visible from Earth during each visit. At their core, comet orbits are elongated ellipses. Unlike the nearly circular orbits of the planets, comet paths are stretched into long, narrow loops. These loops carry comets from the deep cold of the outer solar system into the warm inner regions near the Sun, and then back again into darkness. The degree of elongation varies widely. Some comets travel on relatively modest paths, while others trace arcs so vast that their aphelion lies tens of thousands of astronomical units away. Short-period comets tend to have more compact orbits. Their paths usually remain close to the plane in which the planets orbit, suggesting a shared origin and long history of interaction with planetary gravity. These comets may complete an orbit in as little as a few years, or as long as a couple of centuries. Because they return frequently, astronomers can observe them across multiple generations, tracking how their brightness, structure, and activity evolve over time. Long-period comets behave very differently. Their orbits are enormous and often highly tilted, bringing them into the inner solar system from almost any direction. These comets may spend millions of years far from the Sun, moving slowly through deep space before accelerating rapidly as they fall inward. Their passage near the Sun is brief compared to the immense duration of their full orbit, making each appearance a rare and fleeting event. Some comets follow paths that are nearly parabolic, meaning they are only weakly bound to the Sun. Others move on hyperbolic trajectories, indicating that they are not bound at all. These comets pass through the solar system once, and then continue onward into interstellar space, never to return. Such objects remind us that the solar system is not isolated, but part of a much larger galactic environment. The shape and stability of a comet's orbit depend heavily on gravitational encounters. Close passes by planets can dramatically alter a comet's future. Jupiter, because of its immense mass, exerts the strongest influence. A single close encounter with Jupiter can shorten a comet's orbit, tilt it into a new plane, or fling it outward at high speed. For this reason, Jupiter is often described as a gatekeeper of the inner solar system. These gravitational interactions make comet motion complex and sometimes chaotic. Small differences in a comet's position during a planetary encounter can lead to vastly different outcomes over long periods. Some comets become trapped in stable resonances, returning at predictable intervals. Others experience gradual orbital diffusion, their paths slowly changing until they are either captured or lost. The closest point of a comet's orbit to the Sun is called perihelion. This moment defines the comet's visible life. As it approaches perihelion, solar heating intensifies, driving sublimation and creating large comas and long tails. The closer the perihelion distance, the more violent the activity. For some comets, this passage is gentle. For others, it is catastrophic. Sun-grazing comets represent the most extreme case. These objects pass extraordinarily close to the Sun, sometimes only a few thousand kilometers above its surface. Many are destroyed by tidal forces and intense heat, breaking apart into clouds of vapor and dust. Yet some survive, returning again and again, each passage slowly eroding their nuclei. After perihelion, the comet recedes and activity diminishes. Eventually, the coma collapses, the tails vanish, and the comet becomes inactive once more. It then continues outward toward aphelion, where temperatures are so low that sublimation stops entirely. In this distant phase, the comet may spend tens of thousands or even millions of years drifting slowly through darkness. Comet orbits are also affected by non-gravitational forces. As gas escapes from the nucleus, it produces small but continuous thrusts, similar to tiny natural rocket engines. These forces can slightly alter a comet's speed and direction. Over many orbits, the cumulative effect can noticeably shift the comet's path, changing its predicted return time or even its long-term stability. Because of these effects, comet predictions are never perfectly exact. Even well-studied comets may arrive earlier or later than expected. Their motion reflects a balance between the predictable pull of gravity and the subtle influence of ongoing activity. Over very long timescales, comet orbits evolve. Long-period comets can become short-period ones through repeated encounters. Others gradually lose energy and settle into stable paths, while some are eventually ejected from the solar system entirely. Each outcome is part of a continuous process shaping the population of comets we observe today. The study of comet orbits reveals a solar system that is dynamic and ever-changing. It is a place where gravity, motion, and time interact continuously. Comets move through this system as both participants and witnesses, carrying the imprint of ancient events within their paths. When we watch a comet trace its slow arc across the night sky, we are seeing the visible expression of forces acting over billions of years. Each orbit is a long story written in motion, a quiet reminder that even fleeting lights in the darkness are governed by deep and enduring laws. Comets may appear timeless as they glide through the night sky, but in reality they are constantly changing. Every journey toward the sun alters them in small but meaningful ways. Over long spans of time, these gradual changes can completely transform a comet, reshaping its surface, its activity, and even its identity. When a comet makes its first approach into the inner solar system, it is often at its most pristine. Its surface has never been warmed by intense sunlight, and its outer layers are rich in volatile ices. As heat reaches the nucleus, sublimation begins across wide areas, sometimes explosively. These early passages can produce enormous comas and bright, dramatic tails, making first-time visitors among the most impressive comets ever observed. But this intensity comes at a cost. Each close pass strips material from the nucleus. Gas escapes into space, dust is carried away, and jets carve pits and fractures into the surface. What remains behind is often a darker, less volatile crust, made of dust and organic residue. This crust can partially insulate the comet, reducing activity on later visits and slowly changing how the comet responds to sunlight. Over time, active regions become fewer. Jets concentrate in specific areas where sunlight can penetrate cracks or weak spots. Other regions fall silent, sealed beneath layers of non-volatile material. As a result, the comet's activity becomes uneven and sometimes unpredictable, changing noticeably from one return to the next. Rotation plays an important role in this evolution. As jets erupt, they exert small but persistent forces on the nucleus. These forces can alter the comet's spin rate and orientation. Some comets spin faster with each pass. Others slow down. In some cases, the axis of rotation shifts, changing which regions receive sunlight and which remain in shadow. This rotational stress can be destructive. If a comet spins too quickly, centrifugal forces may exceed the strength of its loosely bound structure. Cracks widen, layers peel away, and pieces may break off entirely. Some comets split into two or more large fragments, each continuing along a similar orbit. Others disintegrate more subtly, shedding smaller pieces over many returns. Fragmentation is not always dramatic. In many cases, it happens gradually. A comet may lose material grain by grain, leaving behind a trail of debris along its orbit. Over time, this debris spreads out into a long, thin stream of particles. When Earth passes through such a stream, the result is a meteor shower. Brief, quiet streaks of light as tiny fragments burn up in the atmosphere. As comets age, their visible behavior often becomes less dramatic. With fewer volatile materials remaining near the surface, sublimation weakens. Comas shrink. Tails become shorter and fainter. Eventually, a comet may cease visible activity altogether. At this stage, it is often described as dormant or extinct. These inactive remnants can look remarkably similar to asteroids. They are dark, rocky, and no longer produce gas or dust. In fact, some objects, currently classified as asteroids, may actually be extinct comets, bodies that have lost their icy surfaces after countless journeys around the sun. This gradual fading highlights an important truth. Comets are not permanent features of the solar system. They represent a temporary phase in the life cycle of small bodies. A single object may begin as a pristine comet, evolve into a weaker, aging one, and eventually become an inert remnant, nearly indistinguishable from other rocky debris. Even so, comets continue to influence the solar system long after their activity fades. The dust they release contributes to the zodiacal cloud, a diffuse disk of particles that fills the inner solar system and reflects sunlight. Their debris shapes meteor showers that humans have observed and recorded for thousands of years, linking modern skies to ancient observations. The rate at which a comet changes depends strongly on its orbit. Comets that pass very close to the Sun lose material rapidly and may survive only a limited number of returns. Others, with more distant perihelia, evolve more slowly and can remain active for much longer periods. Some may survive hundreds or even thousands of passages before becoming inactive. Through this slow process of erosion and transformation, comets act as moving records of solar influence. By comparing young, highly active comets with older, fading ones, scientists can trace how repeated exposure to sunlight reshapes icy bodies over time. In the end, a comet's existence is defined by repetition. Again and again, it approaches the sun, awakens briefly, and retreats into darkness. With each cycle, it gives up a small part of itself, trading brilliance for silence. And through that long, gradual change, comets reveal not only their own fragile nature, but the quiet, persistent forces that shape everything moving through the solar system. To understand why comets matter so much, it helps to imagine the solar system at the very beginning, long before planets had settled into stable orbits. At that time, the sun was young, surrounded by a vast, rotating disk of gas and dust, known as the solar nebula. Within this disk, temperatures varied dramatically. Close to the sun, heat was intense. Farther out, cold dominated, allowing ices to form and survive. In the warmer inner regions of the nebula, Only metals and rocky materials could remain solid. This is where the terrestrial planets, Mercury, Venus, Earth, and Mars, began to take shape. Water and other volatile compounds could not easily condense there. Any ice that formed was quickly vaporized by the sun's heat. Farther from the sun, beyond what is often called the frost line, conditions were very different. Temperatures were low enough for water ice, carbon dioxide, methane, ammonia, and other volatile substances to freeze. Dust grains coated in ice collided and stuck together, gradually growing into larger and larger bodies. These icy building blocks would eventually become the cores of the giant planets, as well as countless smaller objects. Comets formed in these cold outer regions. Unlike planets, which continued to grow and differentiate, comets remained small. Many were scattered outward early in the solar system's history by the gravitational influence of the forming giant planets. In doing so, they were preserved in distant reservoirs like the Kuiper Belt and the Oort cloud, effectively frozen in time. Because of this history, comets are among the most primitive objects we can study. They have undergone very little processing compared to planets and moons. Their interiors still contain material that dates back to the era when the solar system itself was taking shape. When a comet becomes active and releases gas and dust, it is exposing that ancient material directly to observation. This is one of the main reasons scientists are so interested in comets. By analyzing the gases released from their comas, researchers can determine their chemical composition. These measurements reveal not only what comets are made of, but also the conditions under which they formed. Ratios of different isotopes, for example, can act like fingerprints, linking comets to specific regions of the early solar nebula. One of the most important questions comets help address is the origin of Earth's water. Earth formed in a region of the solar system that was likely too warm for large amounts of water ice to condense. Yet today, Earth has vast oceans. This raises the question of where that water came from. One hypothesis suggests that comets delivered water to the early Earth through impacts. During the chaotic early period, known as the Late Heavy Bombardment, countless small bodies collided with the young planets. If even a fraction of these impactors were icy, they could have contributed significant amounts of water. However, the story is complex. Measurements of hydrogen isotopes in some comets show ratios that differ from Earth's oceans. This suggests that comets may not be the sole source of Earth's water, or that only certain types of comets contributed. Other icy bodies, such as water-rich asteroids, may also have played an important role. Beyond water, comets contain organic molecules, carbon-based compounds that are the building blocks of life. These include simple molecules like formaldehyde and more complex ones, such as amino acid precursors. The presence of these compounds suggests that the chemistry needed for life began long before Earth formed. When comets impacted the early Earth, they may have delivered not only water, but also organic material. This influx could have enriched the planet's surface with chemical ingredients that later participated in the development of life. In this way, comets may have influenced biology without ever hosting life themselves. The study of comet composition has been transformed by spacecraft missions. By flying close to comets or even landing on them, scientists have been able to observe their structure and chemistry directly. These missions have revealed that comets are more complex than once thought, with layered interiors, varied surface terrains, and diverse chemical compositions. Such findings reinforce the idea that comets formed across a range of environments within the early solar system. They are not all identical. Each comet carries a unique record of its formation conditions, shaped by its location and history. Comets also provide insight into how the giant planets formed and migrated. The current distribution of comets suggests that planets like Jupiter and Saturn did not remain fixed in place. Instead, they likely moved during the solar system's youth, scattering icy material outward and inward. This migration helped populate the Kuiper Belt and Oort cloud, shaping the comet populations we see today. Without this planetary movement, the solar system would look very different. Comets would be distributed differently, and the delivery of water and organics to the inner planets might have been far less efficient. In this sense, comets act as tracers of ancient planetary motion, preserving evidence of events that occurred billions of years ago. Even today, comets continue to link the present to the distant past. Each time a comet approaches the sun, it releases material that has been locked away since the solar system's formation. Instruments on Earth and in space capture these emissions, allowing scientists to study conditions that no longer exist anywhere else. In the quiet glow of a comet's coma, there is a connection across time. The gases drifting away were once part of the same cloud that formed the sun. The dust grains once floated freely in the nebula, colliding and clumping in the cold darkness. Comets remind us that the solar system is not just a collection of planets, but a dynamic system with deep history. They show us that small, fragile objects can carry enormous scientific importance, preserving information that larger bodies have long since erased. As comets continue their slow journeys, they offer repeated opportunities to study the earliest chapters of our cosmic story. Each return is a brief window into the past, opening and closing again as the comet fades back into darkness. And with every observation, we refine our understanding of how the solar system formed, how Earth became habitable, and how ancient material continues to move through space, unchanged except by the light of the sun. From the moment humans first looked up at the night sky, comets have occupied a special place in our imagination. Long before science provided explanations, comets were noticed, remembered, and woven into stories. They were impossible to ignore. Unlike stars, which returned night after night to the same positions, comets appeared suddenly, moved against the familiar patterns of the sky, and then vanished. This unpredictability made them powerful symbols. In many ancient cultures, the sky was not separate from human life. What happened above was believed to reflect what would happen below. Because comets disrupted the orderly motion of the heavens, they were often interpreted as signs of disruption on Earth. They became associated with change, uncertainty, and events beyond human control. Some of the earliest written records of comets come from ancient China. Court astronomers kept detailed chronicles of celestial phenomena, including comets, eclipses, and planetary motions. These records were not symbolic or poetic. They were systematic observations, noting the comet's position, brightness, color, tail length, and duration. Chinese scholars believed that such events were messages from heaven, warning of political upheaval, natural disasters, or the rise and fall of rulers. In Mesopotamia, comets were recorded alongside omens and astrological interpretations. Clay tablets describe comets as portents that could influence the fate of kings or entire nations. A comet's appearance in a certain part of the sky or at a certain time carried specific meanings within these belief systems. The sky was read like a text, and comets were among its most dramatic symbols. In ancient Greece, thinkers attempted to move beyond purely symbolic interpretations. Philosophers debated whether comets were celestial or atmospheric. Aristotle argued that comets formed in the upper atmosphere from dry vapors that ignited. His authority was so influential that this explanation dominated Western thought for nearly 2,000 years. Because comets were seen as temporary and changeable, they did not fit easily into the idea of a perfect, unchanging celestial realm. Despite this, comets continued to leave strong impressions. Roman writers described them as hairy stars, noting their flowing tails. They were often linked to the deaths of emperors or major political transitions. The appearance of a bright comet was remembered long after it faded from view, preserved in historical accounts and oral tradition. During the Middle Ages in Europe, comets became closely tied to religious interpretation. They were often seen as warnings from God, symbols of divine judgment or calls for repentance. The arrival of a comet could provoke fear, prayer, and speculation. Chroniclers described comets as flaming swords or burning spears suspended in the sky. One of the most famous examples is the comet of 1066, later identified as Halley's Comet. Its appearance was recorded in the Bayeux Tapestry, where it is shown as a blazing object watched by figures pointing upward in alarm. To those who witnessed it, the comet seemed to foreshadow the Norman conquest of England. Whether coincidence or not, the timing ensured the comet's place in history. Across other parts of the world, comets carried different meanings. In some cultures, they were seen not as threats, but as messengers or travelers. Indigenous traditions sometimes interpreted comets as spirits moving through the sky, or as signs marking the passage of time rather than disaster. These interpretations remind us that fear was not the only human response to the unexpected lights above. As observational tools improved, attitudes toward comets slowly began to change. The invention of the telescope allowed astronomers to study comets in greater detail. They could track their motion against the stars and observe changes in their structure over time. Gradually, the idea that comets were physical objects moving through space gained acceptance. A turning point came in the 17th century, when astronomers like Johannes Kepler and Isaac Newton laid the foundations of celestial mechanics. Newton's laws of motion and universal gravitation provided a framework that could explain the paths of planets and comets as well. For the first time, comets could be understood not as omens, but as objects obeying the same physical laws as everything else in the universe. Edmund Halley applied these ideas to comet observations. By comparing historical records, he realized that comets seen in 1531, 1607, and 1682 were likely the same object returning on a regular orbit. He predicted its return in 1758. When the comet appeared as expected, it marked a profound shift in human understanding. Comets were no longer random visitors. They were predictable. This realization did not immediately erase centuries of symbolism, but it began to change how people thought about the sky. Comets became subjects of study rather than fear. Their appearances were anticipated rather than dreaded. As science advanced, comets entered popular culture in new ways. In literature, they became symbols of deep time and cosmic perspective. Writers used comets to evoke feelings of impermanence, reminding readers that human life unfolds within a much larger universe. In art, comets were depicted as graceful arcs of light rather than threatening flames. In the modern era, comets have taken on yet another role, that of scientific targets. Space missions have transformed comets from distant spectacles into physical worlds that can be visited, mapped, and sampled. Images returned from spacecraft have replaced imagination with detail, revealing cliffs, jets, and textured surfaces. These missions have also changed public perception. When people see photographs of a comet's nucleus, irregular and dark, they begin to understand it as a real place rather than a symbol. Comets have become accessible, objects that can be studied and understood. At the same time, comets retain their emotional power. A bright comet in the night sky still draws attention. People step outside, look up, and feel a connection to something ancient and rare. Even with all we know, there is still wonder in watching a comet slowly fade into the distance. Comets also play a role in modern discussions about planetary defense. Because they can cross Earth's orbit, they are studied as potential impact hazards. While the risk from comets is low compared to asteroids, their high speeds and long orbits make them important to monitor. In this context, comets are no longer omens, but objects to be understood and prepared for. The story of comets and humanity is, in many ways, a story of how human understanding evolves. Comets began as mysterious signs in the sky, became objects of fear and fascination, and eventually transformed into subjects of scientific inquiry. Each stage reflects the tools, beliefs, and knowledge available at the time. Yet even now, comets still bridge the gap between science and emotion. They remind us that the universe is not static, that change can appear suddenly and without warning. They connect modern observers to ancient ones, separated by thousands of years, but united by the same experience of looking up and seeing something unexpected. When a comet appears, it is seen by millions of people across the world, each bringing their own thoughts and interpretations. Some see a scientific opportunity, others see beauty, some feel a quiet sense of awe. In that shared moment, comets continue to fulfill one of their oldest roles, drawing human attention upward. As long as humans watch the sky, comets will remain part of our story. They will continue to arrive unannounced, follow their ancient paths, and disappear again into darkness. And each time they do, they will remind us that we are observers in a vast moving universe, connected not only to the present moment, but to all the moments before it. When comets are studied through the lens of modern science, they become far more than beautiful objects in the sky. They act as messengers, carrying information from the earliest moments of the solar system directly into the present. Every observation, every spectrum, and every spacecraft encounter adds another layer to our understanding of how these ancient bodies formed and what they can tell us about our cosmic origins. One of the most important ways scientists study comets is by analyzing the light they emit and reflect. As a comet approaches the sun, gases escaping from its nucleus become energized by sunlight. These gases glow at specific wavelengths, creating a spectral fingerprint that reveals their chemical composition. By studying these spectra, astronomers can identify water vapor, carbon monoxide, carbon dioxide, methane, ammonia, and a wide range of organic molecules. This method allows scientists to study comets without ever touching them. From Earth-based telescopes and space observatories, researchers can track how a comet's composition changes as it warms, how different gases dominate at different distances from the Sun, and how activity varies across the nucleus. These observations reveal that comets are chemically diverse. No two comets are exactly alike. Some comets release large amounts of carbon monoxide, even at great distances from the Sun, suggesting they formed in extremely cold regions. Others show stronger water signatures only when they approach the inner solar system. This diversity hints at a complex, early solar nebula, where temperature, pressure, and chemistry varied from place to place. Beyond gases, dust from comets provides another crucial source of information. Dust grains released into the coma scatter sunlight and emit infrared radiation. By studying this light, scientists can infer the size, structure, and composition of the dust. Many cometary dust particles are rich in carbon and contain complex organic compounds. Some grains appear to be fluffy aggregates, loosely bound clusters rather than solid rocks. These fragile structures support the idea that comets formed gently through slow accumulation of material rather than violent collisions. In some cases, dust grains contain minerals that formed at high temperatures near the young Sun, mixed with ices that formed far away. This surprising combination suggests that material was transported across vast distances during the solar system's formation. Spacecraft missions have taken comet science even further. By flying close to comets, orbiting them, or even landing on their surfaces, spacecraft have transformed comets from distant points of light into detailed worlds. Images returned from these missions reveal rugged landscapes with cliffs, pits, smooth plains, and towering jets of gas and dust. These close-up observations show that comet nuclei are not uniform. Different regions behave differently depending on composition, structure, and exposure to sunlight. Some areas remain quiet, while others erupt with activity. This patchwork behavior explains why comets can change dramatically from one return to the next. Space missions have also allowed scientists to directly sample comet material. Instruments have analyzed gases and dust in situ, confirming the presence of complex organic molecules. In some cases, these molecules resemble the precursors of amino acids, reinforcing the idea that comets could have contributed to the chemical inventory of the early Earth. Perhaps most importantly, spacecraft data have shown that comets are not solid blocks of ice. They are porous, fragile bodies with low densities. Many appear to be loosely bound collections of material, sometimes described as rubble piles. This structure makes them highly responsive to heating, stress, and tidal forces, explaining why fragmentation is so common. Comets also serve as natural laboratories for studying physical processes. The interaction between the solar wind and a comet's coma provides insight into plasma physics. The way dust and gas separate into distinct tails helps scientists understand radiation pressure and electromagnetic forces. Even the way comets rotate and evolve offers clues about how small bodies respond to asymmetric forces. Observations of comet impacts have also been scientifically valuable. When a comet fragment collides with a planet, it provides a rare opportunity to study impact, physics, and planetary atmospheres. Such events remind scientists that comets are active participants in the solar system, not just passive relics. Modern comet studies extend beyond our own solar system. the discovery of interstellar objects passing through our neighborhood suggests that comet-like bodies may be common around other stars. By studying comets here, scientists gain insight into processes that may be universal across planetary systems. Comets also play a role in understanding long-term solar system evolution. Their distribution, composition, and behavior help constrain models of planetary migration and early dynamical instability. Without comets, many aspects of solar system history would remain speculative. Even with all this data, comets retain an element of mystery. Their deep interiors remain largely inaccessible, and each new comet observed brings unexpected behavior. Some brighten suddenly, others fade without explanation. Some fragment, others survive repeated close encounters at the sun. This unpredictability is part of what makes comets so valuable scientifically. They challenge models, force revisions, and reveal new processes. They remind scientists that the solar system is not fully understood, even after centuries of study. As technology advances, new tools will deepen our understanding further. More sensitive telescopes will detect comets at greater distances. Future missions may return samples directly to Earth, allowing laboratory analysis of pristine material. These efforts promise to unlock even more information stored within these ancient objects. In this way, comets act as messengers across time. They carry the chemical and physical record of the solar system's birth, preserved in ice and dust. When they approach the sun, they briefly release that record, allowing modern instruments to read it. Each comet that appears is an opportunity, a chance to observe, to measure, and to learn. And as long as comets continue their slow journeys through space, they will remain among the most important storytellers of our cosmic past. Comets are often spoken of as distant wanderers, objects that belong to the deep reaches of space rather than to Earth's immediate environment. Yet throughout the history of the solar system, comets and Earth have been connected in quiet but meaningful ways. Sometimes that connection has been gentle, delivering dust that burns harmlessly in the atmosphere. At other times, it has been violent, shaping the planet's surface and influencing the course of life itself. From a scientific perspective, comets are Earth-crossing objects. Their elongated orbits frequently intersect the paths of planets. While the vastness of space makes direct collisions rare, the sheer number of comets and the immense spans of time involved mean that impacts are not only possible, but inevitable. In the early solar system, impacts were far more common than they are today. During the period known as the Late Heavy Bombardment, Earth and the other inner planets were struck repeatedly by asteroids and comets. The young Earth's surface was reshaped again and again by enormous collisions, many of which released energies far beyond anything experienced in recorded human history. Comets played a unique role in this process. Because they originate from cold, distant regions, they carry large amounts of ice and volatile material. When a comet impacts a planet, the effects differ from those of a purely rocky asteroid. In addition to the energy of the collision itself, comet impacts release vast quantities of gas and vaporized material into the atmosphere. These early impacts may have contributed to Earth's oceans. As comets struck the surface, their ice was vaporized, adding water vapor to the atmosphere. Over time, as the planet cooled, this water condensed and fell as rain, helping to fill basins and form the first oceans. While comets were likely not the only source of Earth's water, they may have played an important supporting role. Beyond water, comets also delivered organic compounds. Many of the carbon-based molecules found in comets are similar to those needed for prebiotic chemistry. When delivered to the early Earth, these compounds could have accumulated in surface environments, such as shallow seas or tidal pools, contributing to the chemical diversity needed for life to emerge. However, not all impacts were beneficial. Large comet impacts are capable of causing global devastation. A sufficiently large impactor can inject massive amounts of dust and aerosols into the atmosphere, blocking sunlight for months or years. Temperatures drop. Photosynthesis slows or stops. Food chains collapse. These events can trigger mass extinctions. One of the most famous extinction events in Earth's history occurred around 66 million years ago, marking the end of the age of dinosaurs. While this event is most often attributed to an asteroid impact, the possibility of comet involvement has also been explored. Some hypotheses suggest that long-period comets disturbed from distant reservoirs could fragment and increase the rate of impacts during certain periods. Regardless of the exact source, the lesson is clear. Objects from space have repeatedly influenced life on Earth. Comets are part of that story. Even smaller comet fragments can have noticeable effects. As comets shed material along their orbits, they leave behind streams of debris. When Earth passes through these streams, the result is a meteor shower. Most meteors are tiny, no larger than grains of sand, and burn up harmlessly in the atmosphere. Yet their frequency reminds us that Earth is constantly interacting with material from space. Occasionally, larger fragments survive atmospheric entry. These meteorites, though rare from comets compared to asteroids, provide physical samples of extraterrestrial material. Studying them helps scientists understand the composition and structure of small bodies that cross Earth's path. Modern science also considers comets in the context of planetary defense. While asteroid impacts receive more attention, comets present unique challenges. Long-period comets can approach from any direction, often with little warning. Their high speeds make them difficult to intercept, and their unpredictable behavior complicates tracking. For this reason, astronomers monitor the sky continuously, searching for new objects that could pose a threat. Most comets discovered today are harmless, passing far from Earth. Still, the possibility of a future impact cannot be ignored. Despite this risk, comets are not simply harbingers of disaster. Over geological timescales, their influence has been balanced. They have delivered water and organic material, reshaped environments, and occasionally caused destruction. In doing so, they have contributed to the dynamic history of Earth, rather than acting as purely destructive forces. Comets also influence Earth in subtler ways. Dust released by comets contributes to the zodiacal light, a faint glow visible in dark skies after sunset or before sunrise. This dust slowly drifts inward toward the sun, interacting with Earth's atmosphere and adding a constant, gentle influx of extraterrestrial material. Each year, tons of cosmic dust fall to Earth, much of it originating from comets. These particles settle quietly onto land and ocean, becoming part of the planet's surface. Over millions of years, this steady rain of material has added trace elements to Earth's crust and oceans. The relationship between comets and Earth is therefore not defined by single dramatic events, but by continuous interaction. Most of the time, that interaction is subtle and harmless. Occasionally, it is transformative. Looking forward, comets remain objects of both curiosity and caution. Understanding their orbits, composition, and behavior is essential not only for science, but for long-term planetary safety. Each new comet observed improves models and reduces uncertainty. At the same time, comets invite reflection. They remind us that Earth exists within a larger cosmic environment, shaped not only by internal processes, but by interactions with objects from far beyond its surface. The planet's history cannot be separated from the history of the solar system as a whole. When a comet appears in the sky, glowing softly above the horizon, it carries with it this deeper context. It is not merely a spectacle. It is a reminder of ancient collisions, of water delivered from space, of extinctions and renewals, and of the ongoing relationship between Earth and the wider universe. Comets have helped shape the world we live on, sometimes gently, sometimes violently. And as long as they continue their ancient journeys, they will remain part of Earth's story, distant, unpredictable, and deeply influential. Among the countless comets that move through the solar system, a small number have left particularly strong marks on human memory. These are the comets that appeared at pivotal moments, shone with unusual brightness, or returned often enough to be recognized across generations. Their stories combine careful observation, historical coincidence, and the gradual growth of scientific understanding. One of the most well-known of all is Halley's Comet. Its importance does not come from exceptional brightness alone, but from familiarity. Halley's Comet returns roughly every 76 years, making it visible within a human lifetime. For centuries, people observed it without realizing it was the same object returning again and again. Records of Halley's Comet stretch back more than 2,000 years. Ancient Chinese astronomers described its appearance in 240 BCE. It was later recorded by Babylonian observers and by medieval chroniclers in Europe. Each appearance was treated as a separate event, often interpreted as an omen, until patterns began to emerge. The turning point came in the 17th century, when Edmund Halley compared historical records of bright comets. He noticed striking similarities in the comets seen in 1531, 1607, and 1682. Using Newton's newly developed laws of motion, Halley calculated that these were not separate comets, but a single object on a repeating orbit. He predicted its return in 1758. When the comet appeared as predicted, it marked a defining moment in astronomy. It was proof that comets followed the same physical laws as planets. The comet was later named in Halley's honor, and its returns in 1835, 1910, and 1986 were carefully observed with increasingly advanced instruments. Another famous visitor was the Great Comet of 1811. This comet remained visible to the naked eye for many months and developed a vast, luminous coma. It appeared during a time of global conflict and uncertainty, including the Napoleonic Wars, and was widely discussed in both scientific and popular circles. Artists, poets, and scientists alike documented its presence. The Great Comet of 1843 was notable for its dramatic approach to the sun. It passed extremely close, becoming a brilliant sun grazer. Its tail stretched across much of the sky, visible even in daylight. The comet's sudden appearance and extraordinary brightness left a deep impression on observers around the world. In 1910, Halley's Comet returned during a period of growing scientific literacy, but also widespread public anxiety. Spectroscopic analysis had revealed the presence of cyanogen gas in comet tails. When Earth was predicted to pass through Halley's tail, sensational headlines warned of poisoning. Entrepreneurs sold comet pills and bottled air. In reality, the gas was far too thin to have any effect, and the event passed harmlessly. The 20th century also saw comets captured in photographs for the first time. Advances in astrophotography allowed astronomers to record fine details in comet tails and comas, revealing complex structures shaped by solar radiation and magnetic fields. These images helped transform comets from mysterious apparitions into objects of scientific study. One of the most widely observed modern comets was Comet Hale-Bopp, which appeared in 1997. It was visible for more than a year and reached exceptional brightness. Its long visibility allowed millions of people to observe a comet firsthand, many for the first time in their lives. Hale-Bopp became a cultural event, widely reported and discussed. Hale-Bopp also demonstrated the dual nature of comets in the modern age. While most people viewed it with wonder, a small group misinterpreted its appearance, linking it to conspiracy theories and tragic events. This contrast highlighted how comets continue to provoke strong reactions, even in an era dominated by scientific explanation. Other notable comets include Comet Hyakutake in 1996, which passed unusually close to Earth, and Comet McNaught in 2007, which became one of the brightest comets in decades, especially in the southern hemisphere. Each of these comets offered unique opportunities to study comet behavior under different conditions. Some famous comets are remembered not for their brilliance, but for their disappearance. Comet Ieson, anticipated as a potentially spectacular sight in 2013, disintegrated as it approached the Sun. Its breakup provided valuable data on how comets respond to extreme heating and tidal stress, even as it disappointed skywatchers. These famous comets serve as milestones in both human history and scientific progress. Each appearance reflects the knowledge and tools available at the time. Early observers recorded comets with fear or reverence. Later generations measured their positions and predicted their returns. Modern astronomers analyzed their chemistry and structure in detail. Famous comets also remind us that each object is unique. No two comets behave in exactly the same way. Some survive close passes to the Sun repeatedly. Others fragment or fade. Some return reliably. Others vanish after a single appearance. Together, these stories form a timeline of discovery. They show how comets have moved from the realm of myth into the domain of science without losing their ability to inspire awe. Even today, the announcement of a bright new comet captures public attention, echoing reactions that stretch back thousands of years. When the next great comet appears, it will join this long tradition. It will be photographed, analyzed, shared across the world in real time. And yet, in that moment of collective attention, it will fulfill the same role it always has, reminding humanity of the vastness of space, the passage of time, and the quiet persistence of these ancient travelers. For most of human history, comets could only be observed from a distance. Even with telescopes, they remained blurry, shifting shapes, more like apparitions than worlds. That changed in the late 20th century, when humanity began sending spacecraft to meet comets face to face. These missions transformed comets from abstract celestial objects into physical places with landscapes, structure, and complexity, The first close encounters were brief flybys. Spacecraft passed through comet comas at high speed, sampling gas and dust as they went. These early missions confirmed what scientists had long suspected. Comets are active, dynamic objects. Jets of gas erupt from localized regions. Dust grains vary widely in size and composition. The coma is far from uniform, shaped by sunlight, rotation, and internal structure. One of the earliest milestones came when spacecraft encountered Halley's Comet during its 1986 return. Multiple probes from different space agencies flew past the comet, capturing the first close-up images of a nucleus. What they revealed was surprising. Instead of a bright, icy surface, Halley's nucleus was dark, irregular, and unevenly active. Jets erupted from specific regions, while much of the surface remained quiet. This discovery reshaped comet science. It showed that comets are not uniformly icy spheres, but complex bodies with varied terrain and localized activity. The darkness of the surface suggested that comets develop insulating layers of dust and organic material over time, protecting underlying ice until fractures or weak spots allow gas to escape. Later missions built on this foundation. Spacecraft began to study comets over longer periods, rather than brief flybys. This allowed scientists to observe how activity changed as a comet approached and receded from the sun. These missions revealed that comet behavior evolves continuously, driven by rotation, solar heating, and internal structure. One of the most ambitious missions involved placing a spacecraft into orbit around a comet and deploying a lander onto its surface. For the first time, humanity touched a comet directly. Images returned from the surface showed a rugged alien landscape. Cliffs, boulders, smooth plains, and fractured crusts shaped by sublimation and collapse. Instruments detected organic molecules, complex chemistry, and extremely low density. The comet was not solid rock, but a fragile assembly of material with large internal voids. This explained why comets are so easily reshaped and why fragmentation is common. Sampling missions have also collected comet dust and returned it to Earth for laboratory analysis. These samples revealed a surprising mix of materials. Some grains formed at extremely high temperatures near the young sun, while others formed in deep, cold, far away. Their presence together confirmed that the early solar system was a place of extensive mixing, with material transported across vast distances. Together, these missions confirm that comets are not simple leftovers. They are records, layered, altered, and shaped by billions of years of interaction with the solar system. Each mission added depth, turning comets into some of the most informative objects ever studied. For a long time, comets were thought to be unique to our solar system. They were seen as remnants of our own planetary formation, shaped by our sun and our planets. That view began to change when astronomers detected objects passing through the solar system that did not belong to it. These interstellar visitors followed paths that could not be explained by the sun's gravity alone. Their trajectories were hyperbolic, meaning they were not bound to the sun and would never return. They were travelers from other star systems, passing through our cosmic neighborhood by chance. Some of these objects behaved like comets. They released gas, formed comas, and responded to solar heating. Others appeared more asteroid-like, showing little visible activity. Together, they suggested that comet-like bodies may be common throughout the galaxy. This realization expanded the significance of comets dramatically. If comets exist around other stars, then the processes that formed our solar system are not unique. Planetary systems elsewhere likely possess their own reservoirs of icy bodies, their own Kuiper belts and Oort clouds, shaped by their stars and planets. Studying comets in our own solar system therefore provides insight into planetary systems across the galaxy. The chemistry found in comets here may be similar to that found elsewhere. Organic molecules, water ice, and primitive material may be widespread, increasing the likelihood that habitable conditions arise in many systems. Interstellar objects also offer a rare opportunity. They provide direct samples of material formed around other stars. Even brief observations can reveal composition, structure, and behavior that differ from native solar system objects. Each detection opens a new field of comparative planetary science. As detection technology improves, astronomers expect to find many more interstellar visitors. Some may be captured temporarily by the sun's gravity. Others may pass through too quickly for detailed study. Future missions may one day be designed specifically to intercept such objects. In this broader context, comets become ambassadors of planetary formation itself. They are not just relics of our past, but representatives of a process that unfolds around stars throughout the galaxy. Despite centuries of observation and decades of spacecraft missions, comets remain only partially understood. Their deep interiors are largely inaccessible. Their long-term evolution is still modeled rather than observed. Each new comet continues to surprise scientists with unexpected behavior. The future of comet exploration focuses on depth rather than distance. Instead of brief encounters, future missions aim to stay with comets longer, observe them across multiple orbits, and probe beneath their surfaces. Concepts include drilling into nuclei, deploying long-lived landers, and returning pristine samples to Earth. Sample return missions are particularly valuable. Material brought back under controlled conditions can be analyzed with techniques far more sensitive than any spacecraft instrument. Such samples could reveal subtle isotopic ratios, complex organic chemistry, and clues to processes that occurred before planets existed. Another area of focus is planetary defense. Improved surveys will detect more comets earlier, providing better understanding of potential impact risks. While catastrophic impacts are rare, preparation depends on knowledge. Studying comet structure helps determine how they might respond to deflection attempts if one were ever found on a collision course. Comets will also play a role in understanding habitability beyond Earth. Their chemistry offers insight into how water and organic molecules are distributed through planetary systems. By comparing comet compositions across different populations, scientists can reconstruct how material moves during planet formation. Even without spacecraft, comets will continue to be valuable targets. New telescopes will detect them farther from the sun, observing activity at unprecedented distances. These observations will reveal how different ices activate and how early stages of comet behavior unfold. For the public, comets will remain among the most captivating objects in the sky. No matter how much is learned, their appearances retain a sense of rarity and connection to deep time. A bright comet still stops people in their tracks, drawing eyes upward just as it did thousands of years ago. In the end, comets occupy a unique position in science and culture. They are ancient yet active, fragile yet influential. They connect the formation of planets to the emergence of life, the distant past to the present moment, and our solar system to the wider galaxy. As long as comets continue their slow journeys through space, they will continue to offer opportunities to observe, to learn, and to reflect. They are reminders that even the smallest objects can carry the longest stories, written not in words, but in ice, dust, and motion across the stars. At first glance, a comet appears simple. From Earth, it looks like a bright head surrounded by mist with a tail trailing behind it. Even early scientific descriptions often reduced comets to basic components: ice, dust, and rock. But as observations improved and spacecraft began to study comets up close, this simplicity vanished. What emerged instead was a picture of remarkable internal complexity. A comet's nucleus is not a solid object in the way a mountain or an asteroid is solid. Measurements of mass, volume, and gravity have shown that comet nuclei have extremely low densities. This means that a large fraction of their interior is empty space. Rather than being compact, comets are loosely assembled, with countless voids, pores, and channels running through them. This porous structure is a direct consequence of how comets formed. In the early solar system, tiny grains of ice and dust gently collided and stuck together at very low speeds. There was no intense heating, melting, or compression. The material accumulated slowly, preserving fragile structures that would never survive inside a planet or even a large asteroid. As a result, comets are among the most delicate large objects in the solar system. Inside a comet, this porosity creates a complex internal environment. Gas produced by sublimation does not simply escape straight from the surface. Instead, it can travel through internal channels, migrate sideways beneath the crust, and build up pressure in unexpected locations. When that pressure finally finds a way out, it can erupt violently, producing jets that burst from specific regions of the surface. This is why comet activity is often highly localized. Rather than sublimating evenly across the entire surface, comets tend to release gas from discrete vents. Some areas remain quiet, sealed beneath layers of dust and non-volatile material, while others erupt repeatedly. These active regions can persist for many orbits, slowly reshaping the comet's exterior. Over time, the surface of a comet develops layers. The uppermost layer is often a crust, made mostly of dust and organic residue. This crust forms as ice sublimates away, leaving behind heavier material that does not evaporate easily. The crust can act as an insulating blanket, reducing further sublimation beneath it. Below this crust lies more pristine material. These deeper layers contain higher concentrations of volatile ices that have never been exposed to sunlight. In some comets, these layers may have remained untouched since the solar system formed. They represent a frozen archive, preserving the original composition of the early solar nebula. Thermal energy from the sun penetrates a comet very slowly. During a single pass near the sun, heat may only reach a depth of a few centimeters or meters. Deeper layers remain frozen. Over many orbits, however, thermal waves gradually move inward. This delayed heating can cause sudden changes in activity long after a comet has begun returning regularly. A comet may appear stable for centuries, then suddenly brighten, fragment, or erupt when heat finally reaches a volatile-rich layer buried deep inside. These delayed responses are one reason comet behavior can be so difficult to predict. The surface does not always reflect what is happening within. The layered structure of comets also leads to collapse and surface reshaping. When ice sublimates beneath the crust, it can leave behind empty cavities. Eventually, the overlying material can no longer support itself. It collapses, forming pits, sinkholes, and steep cliffs. Spacecraft images have revealed dramatic landscapes shaped by these processes. Sheer walls hundreds of meters high, fractured plains, and smooth deposits formed by falling debris. These collapses can expose fresh ice directly to sunlight, triggering new jets and bursts of activity. In this way, a comet's internal structure and surface evolution are tightly linked. Each change feeds into the next, creating a constantly evolving object rather than a static one. The weak internal cohesion of comets also explains why they are prone to fragmentation. Unlike solid rock, a comet nucleus is held together by weak forces. Thermal stress, rotational stress, or tidal forces during close planetary encounters can exceed this fragile strength. When that happens, cracks propagate rapidly, and the nucleus can split apart. Some comets break cleanly into large fragments that continue traveling together along similar orbits. Others disintegrate into clouds of debris. In extreme cases, a comet can dissolve almost completely, leaving behind only a dust trail marking where it once passed. Impacts affect comets very differently than they affect asteroids. A collision that might produce a crater on a dense asteroid can shatter a comet or trigger widespread internal collapse. Even small impacts can have outsized effects if they disrupt internal pathways or expose volatile-rich layers. This fragile structure has important implications beyond pure science. Any attempt to alter a comet's trajectory, whether for research or planetary defense, would need to account for its weakness. Applying force to a porous, loosely bound object risks breaking it apart rather than moving it as a single body. Understanding comet interiors therefore requires a shift in perspective. Comets are not icy rocks. They are evolving systems shaped by gentle formation, extreme cold, and repeated exposure to sunlight. Their internal structure is a record of that history, written in layers, voids, and fractures. Every jet, collapse, and outburst is connected to something hidden beneath the surface. When a comet changes suddenly, it is often revealing a process that has been unfolding quietly inside for thousands or millions of years. In this sense, comets are like time capsules that occasionally crack open. Each eruption exposes material that has not seen sunlight since the birth of the solar system. Each collapse reveals another layer of internal history. And with every close approach to the sun, the structure of the comet shifts slightly, carrying it further along its long, fragile evolution. When we observe a comet's changing shape and behavior, we are not just seeing surface activity. We are watching the slow interaction between heat, structure, and time, a delicate balance that defines what a comet truly is. Even after centuries of observation and decades of spacecraft encounters, comets remain among the least predictable objects in the solar system. They brighten unexpectedly, fade without warning, fragment far from the sun, or survive encounters that should tear them apart. Each surprise reveals how much complexity is hidden inside bodies that, from a distance, seem simple. One reason comets continue to surprise scientists is that their behavior is controlled by multiple processes acting at once. Distance from the sun matters, but it is only one factor. Rotation, orientation, internal structure, composition, and surface evolution all play roles. A A comet approaching the Sun at the same distance on two different orbits may behave very differently simply because it is rotated differently or because internal pathways have shifted. Rotation is especially important. As a comet spins, different regions are exposed to sunlight at different times. If a volatile, rich area rotates into continuous sunlight, activity can increase suddenly. Jets can intensify, brightness can rise sharply, and the comet's appearance can change over days or even hours. If that same region later rotates into shadow, activity may drop just as quickly. Rotation itself is not constant. Jets act like tiny thrusters, slowly altering the comet's spin rate and axis. Over time, these changes accumulate. A comet that once rotated steadily may begin to wobble or tumble. This chaotic rotation can expose new regions to sunlight in unpredictable ways, triggering bursts of activity that defy simple models. Composition adds another layer of complexity. Not all ices behave the same way. Water ice sublimates relatively close to the Sun, but carbon monoxide and carbon dioxide can sublimate at much greater distances. This means some comets become active far beyond Jupiter's orbit, long before water ice should respond to solar heating. When this happens, comets can develop comas and tails in regions where activity was once thought impossible. These distant activations force scientists to revise assumptions about how heat moves through a comet and how different materials are distributed inside it. Fragmentation is another major source of surprise. Some comets split gradually, shedding pieces over multiple returns. Others appear stable for centuries, then suddenly break apart in a single pass. Some fragment close to the Sun, while others do so far away, where heating should be minimal. These differences reflect variations in internal strength and structure. A comet with many internal fractures may hold together for a long time until stress finally aligns in a way that causes failure. Another comet may be held together by only weak bonds, ready to fall apart with little warning. From the outside, these internal differences are nearly invisible. Solar activity also plays a role. Changes in the solar wind, bursts of charged particles, and shifts in the Sun's magnetic field can interact with a comet's coma and tail. These interactions can cause sudden changes in tail shape, disconnections, or rapid variations in brightness. While these effects do not always alter the nucleus itself, they change what observers see. Even the same comet can behave differently from one return to the next. Each pass near the Sun reshapes the surface. Active regions migrate, crusts thicken or collapse, and internal pathways evolve. By the time a comet returns, it is not quite the same object it was before. Its history matters. This ongoing evolution makes long-term prediction difficult. Models can describe general behavior, but they struggle to capture the fine details that produce dramatic changes. A small collapse beneath the surface, a newly opened fracture, or a shift in rotation can all produce outsized effects. These surprises are not failures of understanding. They are evidence that comets are dynamic systems rather than inert relics. Each unexpected event reveals a new process or interaction, refining scientific models and expanding knowledge. Comets also remind scientists of the limits of observation. Most of a comet's life is spent far from the Sun, inactive and invisible. Changes may be occurring internally during these long periods of darkness, only becoming visible when the comet returns to sunlight. By the time activity is observed, the processes that caused it may already be far advanced. This is why comets continue to reward careful, patient observation. Each return adds a data point. Each unexpected behavior becomes a clue. Over time, patterns emerge, even if complete predictability remains elusive. In this way, comets remain active participants in discovery. They resist simplification. They challenge assumptions. They behave just differently enough to keep science alert. And perhaps that is part of their enduring appeal. Comets are ancient, but they are not static. They are fragile, but capable of dramatic change. They follow precise orbits, yet behave unpredictably along the way. As long as comets continue their journeys, they will continue to surprise, revealing new details about their nature, the solar environment they move through, and the subtle forces that shape small bodies over deep time. Comets exist on timescales that are difficult to grasp. While human lives are measured in decades and civilizations in centuries, comets move to rhythms set by tens of thousands, millions, or even billions of years. To understand a comet properly is to step outside ordinary time and adopt a perspective shaped by deep cosmic history. Most comets formed more than 4.5 billion years ago, during the earliest stages of the solar system. At that time, the sun was still gathering mass, and planets were only beginning to take shape. Comets condensed from the same cloud of gas and dust that formed everything else. Yet unlike planets, they never melted, differentiated, or underwent major internal restructuring. They remained small, cold, and fragile, preserving conditions that no longer exist anywhere else. From the moment they formed, comets entered long periods of isolation. Many were scattered outward by the growing giant planets and stored in distant reservoirs. There, far from the sun, they drifted quietly for immense spans of time. Entire geological eras on Earth passed, while a single comet completed only a fraction of one orbit. When a comet finally returns to the inner solar system, its appearance is brief. The bright coma and tail that capture human attention may last only weeks or months. Compared to the comet's total lifetime, this is an instant, a fleeting awakening after millions of years of darkness. This contrast between long dormancy and brief activity defines a comet's existence. For most of its life, a comet is invisible, inactive, and unchanged. Its active phase is short, intense, and transformative. Each close approach to the sun alters it slightly, carving away material, reshaping its surface, and advancing it along a slow path toward dormancy. Over many returns, this process accumulates. Layers are stripped away. Volatile materials are depleted. Activity weakens. Eventually, the comet may no longer produce a visible coma or tail. At that point, it becomes a quiet remnant, still following its orbit, but no longer announcing its presence in the sky. Some comets reach this state after only a handful of close passes. Others survive hundreds or thousands of orbits before fading. The difference depends on their size, composition, and orbital path. Comets that pass very close to the sun age quickly. Those with more distant perihelia can persist far longer. From a deep time perspective, comets are not permanent features of the solar system. They are transitional objects, slowly moving from one state to another. New comets are constantly being released from distant reservoirs, while older ones fade or are lost. The population we observe today is only a snapshot of an ongoing process. Comets also provide a bridge between past and present. Ancient observers recorded comet appearances long before modern science existed. These records allow astronomers to trace comet orbits backward in time, connecting present-day observations to events witnessed thousands of years ago. Few natural phenomena offer such continuity. In this way, comets link human history to cosmic history. A comet observed today may be the same object seen by ancient astronomers, medieval chroniclers, and early scientists. Each generation saw it differently, interpreted it differently, yet all witnessed the same traveler following the same ancient path. Looking forward, comets will continue their journeys long after current civilizations are gone. Some will eventually be ejected from the solar system by gravitational encounters. Others will collide with planets or the sun. Many will simply fade into inert objects, quietly circling until disrupted by chance. New comets will replace them. Distant disturbances will send fresh objects inward, beginning the cycle again. The solar system will continue to recycle its small bodies, maintaining a balance between creation, evolution, and loss. From the longest possible perspective, comets remind us that the solar system is not static. It is a dynamic system shaped by motion and time. Even objects that appear unchanged are slowly evolving, responding to forces that act patiently over immense durations. When a comet appears in the night sky, it is tempting to think of it as a momentary event. In reality, it is the visible tip of a story that began billions of years ago and will continue long after the light fades. That brief glow is a signal, a reminder that ancient material has returned, briefly interacting with sunlight before retreating again. Comets also challenge the human sense of permanence. Mountains erode, continents drift, and species rise and fall, yet comets outlast them all. They are older than any landscape on Earth and will remain long after current ones disappear. In their slow, looping paths, comets trace the architecture of the solar system itself. Their orbits map gravitational influences, planetary migrations, and the boundaries between bound and unbound space. To follow a comet's path is to follow the shape of time as much as space. Ultimately, comets offer perspective. They remind us that our moment in the universe is brief, but connected to a much larger story. They show that fragile objects can endure, that change does not require speed, and that the deepest histories are often written quietly. When a comet fades back into darkness, it does not end its story. It simply continues it out of sight, carrying with it the accumulated history of every pass, every jet, every collapse. And somewhere far in the future, it may return again, unchanged enough to be recognized, changed enough to surprise. That is the long view of comets. Ancient travelers moving patiently through time, revealing just enough of themselves for us to glimpse the scale of the universe and our place within it. No comet lasts forever. However ancient and enduring they may seem, every comet is moving toward an ending shaped by the same forces that once brought it to life. These endings are not sudden in most cases. They unfold slowly across countless orbits through erosion, fragmentation, and quiet fading. To understand comets fully, it is necessary to understand how they disappear. The most common fate of a comet is gradual exhaustion. Each time a comet approaches the sun, it loses a small portion of its mass. Gas escapes. Dust is lifted away. Volatile ices near the surface are depleted. Over time, the layers capable of producing visible activity become thinner and more isolated. As this happens, the comet's behavior changes. Early in its life, a comet may display widespread activity with multiple jets erupting across its surface. Later, activity becomes confined to a few remaining regions. Eventually, even those fall silent. The comet still follows its orbit, but it no longer forms a coma or tail. To an observer, it has vanished. At this stage, the comet is often described as dormant or extinct. It has not disappeared physically, but it has lost the features that made it recognizable as a comet. What remains is a dark, inert body, often indistinguishable from an asteroid. Many near-Earth asteroids are thought to be extinct comets, objects that once blazed across the sky, but now move quietly and unnoticed. Some comets reach this state quickly. Those that pass very close to the Sun experience intense heating and rapid mass loss. A few dozen close encounters may be enough to strip away most volatile material. Others with more distant perihelia can remain active for thousands of orbits, aging far more slowly. Another common ending is fragmentation. As comets lose mass, their already weak structure becomes more fragile. Cracks widen, internal stresses accumulate, rotational forces increase as jets alter spin rates. Eventually, the nucleus may no longer be able to hold itself together. When it fails, the breakup can be gentle or catastrophic. In gentle fragmentation, a comet splits into a few large pieces that continue traveling along similar paths. Each fragment may develop its own coma and tail, briefly increasing the comet's apparent brightness. Over time, these fragments drift apart and evolve independently, each following its own shortened lifespan. In catastrophic fragmentation, the nucleus disintegrates into a cloud of debris. The comet may fade rapidly, leaving behind only a diffuse dust trail. To observers, it can appear as if the comet simply vanished. In reality, it has been spread out along its orbit, becoming part of a meteoroid stream. These debris streams persist long after the comet itself is gone. When Earth passes through them, meteor showers occur. In this way, a comet can continue to affect Earth for thousands of years after its physical nucleus has disappeared. The comet's end becomes a new beginning in another form. Some comets meet a more dramatic fate: collision. A comet may collide with a planet, a moon, or the Sun itself. Impacts with planets are rare but significant. When they occur, they release enormous energy, reshaping surfaces and atmospheres. Even impacts with gas giants leave observable scars, briefly altering cloud patterns and atmospheric chemistry. Collisions with the Sun are more common. Sun-grazing comets frequently pass so close that they are torn apart by heat and tidal forces. Many do not survive perihelion. They are vaporized, fragmented, or stretched into streams of gas and dust that spiral into the solar atmosphere. Another possible ending is ejection. Gravitational encounters, especially with Jupiter, can accelerate a comet to escape velocity. When this happens, the comet is no longer bound to the Sun. It leaves the solar system entirely, becoming an interstellar object. It may wander through the galaxy indefinitely, passing near other stars or drifting through deep space forever. From the comet's perspective, this is not destruction, but exile. The object remains intact, carrying the chemical and structural record of its origin far beyond its birthplace. In this way, comets from our solar system may already be traveling through interstellar space, just as objects from other systems occasionally pass through ours. Each of these endings reflects the same underlying truth. Comets are temporary expressions of deeper processes. They are not static relics, but evolving bodies shaped by motion, heat, and gravity. Their brilliance is fleeting, not because they are unimportant, but because they are fragile. Importantly, comet endings are not failures of survival. They are part of a cycle. As old comets fade, fragment, or are lost, new ones are released from distant reservoirs. The solar system maintains a steady exchange between its deep outer regions and its inner space. From a long-term perspective, comets are continuously recycled. Material lost from one comet becomes part of dust clouds, meteor streams, planetary surfaces, or interstellar space. That material may one day contribute to the formation of new bodies elsewhere. When a comet disappears from view, its story does not truly end. It continues in altered form, as dust, as fragments, as a silent remnant, or as a traveler beyond the sun's reach. Its visible life is only one chapter in a much longer narrative. Understanding how comets end completes the picture of what they are. They are born quietly, awaken briefly, change constantly, and eventually fade. Their endings are as varied as their journeys, shaped by the same forces that guide everything moving through the solar system. And in those endings, comets leave traces, subtle, persistent reminders that even the most fleeting lights in the sky can have lasting consequences. Comets are often described as messengers, but what they deliver is not a single piece of information. Instead, they offer lessons about matter, motion, time, and the way complex systems evolve. By studying comets, scientists gain insight not only into these small icy bodies, but into the broader workings of the universe itself. One of the most fundamental lessons comets teach is that the universe preserves its history unevenly. Large bodies like planets are constantly reshaped. Their interiors heat up, their surfaces melt, differentiate, erode, and recycle. Much of their earliest history is erased. Comets, by contrast, remain small and cold. Because of this, they preserve conditions from the earliest stages of planetary formation. This tells us something important about how information survives in the universe. The smallest, most fragile objects often carry the longest memories. In this sense, comets act as archives. They show that understanding the past does not always require studying the biggest or most dramatic objects. Sometimes it requires paying attention to what has changed the least. Comets also demonstrate how structure emerges from gentle processes. They formed not through violent collisions, but through slow accumulation. Their porous interiors, delicate bonds, and layered compositions reflect this quiet origin. This challenges the idea that complexity always arises from force or intensity. In the universe, slow and subtle processes can be just as powerful. The way comets move also teaches us about gravity. Their elongated orbits trace the shape of gravitational influence across vast distances. Long-period comets, in particular, reveal how weak forces accumulate over time. A slight nudge from a passing star, a gentle tidal pull from the galaxy, or a distant planetary encounter can redirect an object across the entire solar system. This sensitivity highlights the interconnectedness of cosmic systems. The solar system does not exist in isolation. It responds to its environment. Comets, especially those from distant reservoirs, make this interaction visible. Their paths encode information about forces acting far beyond the planets. Comets also teach us about energy exchange. When sunlight reaches a comet, energy is absorbed, transformed, and released. Ice sublimates, gas expands, dust accelerates. These processes are small in scale, yet they follow the same physical laws that govern stars, atmospheres, and galaxies. By studying comets, scientists observe these laws, operating in a clean, relatively simple environment. The interaction between comets and the solar wind provides lessons about plasma physics. Charged particles streaming from the sun interact with cometary gases, creating ion tails, magnetic boundaries, and complex flow patterns. These interactions mirror processes occurring on much larger scales, such as those around planets, stars, and even entire galaxies. In this way, comets function as natural laboratories. They allow scientists to study fundamental physics without the complications present in larger, more energetic systems. The lessons learned from comets can be applied broadly, improving understanding across astrophysics. Comets also reshape how scientists think about planetary systems beyond our own. The discovery of interstellar objects suggests that comet-like bodies are common around other stars. If comets form wherever planets form, then the processes observed here may be universal. Water, organic molecules, and primitive material may be widespread throughout the galaxy. This has profound implications. It suggests that the ingredients for habitability are not rare. They may be distributed naturally as part of planet formation itself. Comets, in this sense, help explain how complexity can arise repeatedly in different environments. Another lesson comets teach is humility. Despite advanced technology, many aspects of comet behavior remain unpredictable. This reminds scientists that natural systems often resist complete understanding. Models can approximate, but reality retains nuance. Each comet observed adds knowledge, but also raises new questions. Comets also teach patience. Their most important stories unfold over long periods. A single observation captures only a moment. Meaning emerges through repetition, comparison, and long-term study. This mirrors how understanding grows in science more generally, slowly, cumulatively, through persistence. From a broader perspective, comets teach us about scale. They connect the smallest grains of dust to the largest structures in space. A dust particle released from a comet may eventually fall to Earth. A gravitational disturbance in the galaxy may redirect a comet inward. These connections span vast differences in size and distance. Comets also remind us that change does not require immediacy. A comet may spend millions of years drifting quietly, then undergo dramatic transformation in a matter of weeks. The universe often works this way. Long periods of stability punctuated by brief moments of intensity. Even culturally, comets offer lessons. Human responses to comets have evolved from fear to fascination to understanding. This progression reflects how knowledge transforms perception. What was once seen as a threat becomes a subject of study, then a source of wonder grounded in comprehension. In the end, comets teach us that the universe is both ancient and active, fragile and enduring. They show that small objects can carry immense significance, that time operates on scales far beyond human experience, and that understanding emerges through careful attention to detail. When we study comets, we are not just learning about icy bodies in space. We are learning how the universe remembers, how it evolves, and how simple materials can participate in stories that span billions of years. Comets pass through our skies briefly, but the lessons they carry remain. They invite us to think slowly, to look carefully, and to recognize that even the quietest travelers can illuminate the deepest truths about the cosmos. In the modern world, Comets are no longer surprises in the way they once were. They are discovered years, sometimes decades, before their closest approach to the sun. Their paths are calculated. Their brightness is estimated. Astronomers issue predictions, updates, and alerts. And yet, despite all this preparation, comets still retain a quiet unpredictability that keeps them suspended between certainty and wonder. Modern comet discovery begins far from the naked eye. Automated sky surveys scan the heavens every clear night, comparing images taken minutes or days apart. When a faint object shifts position against the background stars, it is flagged for further study. At first, a newly discovered comet may appear as nothing more than a small smudge of light, barely distinguishable from noise. As observations accumulate, its orbit becomes clearer. Astronomers determine whether it is a short-period comet returning on a known path or a long-period visitor entering the inner solar system for the first time. With this information, anticipation begins. How bright will it become? How close will it pass? Will it survive perihelion? These questions are never answered with complete confidence. Brightness predictions depend on many variables: size, composition, rotation, and how much volatile material lies near the surface. A comet expected to become spectacular may remain faint. Another predicted to be modest may suddenly flare into prominence. Even today, comets resist perfect forecasting. For professional astronomers, comets are opportunities. Each new comet offers a chance to test models, gather data, and refine understanding. Spectrographs are aimed, radio telescopes listen for faint emissions. Space-based observatories track activity beyond the reach of Earth's atmosphere. Together, these observations build a multi-layered picture of each visitor. For amateur astronomers, comets hold a different appeal. They are among the few dynamic celestial objects that can be followed night after night with modest equipment. A comet's motion is visible. Its shape changes. Its tail grows, curves, fades, and sometimes splits. Observing a comet is not about capturing a single perfect image, but about watching a slow transformation unfold. This accessibility has kept comets woven into human experience, even as science advanced. Unlike distant galaxies or subtle cosmic phenomena, comets remain personal. They can be seen from backyards, quiet fields, and dark coastal skies. They reward patience rather than precision. There is also a temporal aspect to observing comets that sets them apart. A planet returns to the same position predictably. A star remains fixed. A comet does not. Miss it, and the opportunity may be gone forever. Some comets will not return for thousands of years. Others will never return at all. This knowledge changes how comets are experienced. There is a sense of impermanence built into every observation. The comet is here now, but it will leave. The sky will return to its familiar patterns, and the visitor will be gone. Even in an age of constant information, this impermanence matters. Comets also play a role in shaping how people think about time. Their long orbits stretch human imagination. A comet observed today may have last passed through the inner solar system before agriculture began, before cities existed, before humans recorded history. To see such an object is to intersect briefly with deep time. This perspective can be grounding. It places human concerns within a larger context. Comets remind observers that the universe has been active long before modern civilization and will remain so long after it. There is also a quiet discipline in comet observation. Comets do not demand attention. They move slowly. They brighten gradually. They reward repeated visits rather than instant gratification. In this way, they encourage a slower relationship with the sky, one based on return, familiarity, and subtle change. Culturally, comets have shifted from symbols of fear to markers of shared experience. When a bright comet appears, images circulate across the world. People step outside together, post photographs, and exchange impressions. The response is global yet personal. Despite this connectivity, the experience remains essentially ancient. A human looks up at the night sky and sees something moving where nothing moved before. That simple act links modern observers to those who watched comets thousands of years ago. There is also an emotional neutrality to comets that sets them apart from other cosmic events. An eclipse is dramatic but brief. A meteor is sudden and fleeting. A supernova is distant and abstract. A comet lingers. It stays long enough to become familiar, yet never long enough to feel permanent. This balance between presence and absence gives comets their distinctive tone. They are neither background nor spectacle alone. They occupy an in-between space. From a scientific standpoint, living with comets also means learning to accept uncertainty. Even with advanced instruments, some aspects of comet behavior remain unknowable until they happen. A nucleus may fragment unexpectedly. Activity may shut down without warning. These events are not failures of prediction, but expressions of natural complexity. This acceptance of uncertainty is part of what keeps comet science active. Each comet adds data, but also variability. Patterns emerge, but exceptions persist. Comets resist being reduced to averages. Looking ahead, the relationship between humans and comets will likely deepen rather than fade. New surveys will discover comets earlier. Future missions may escort comets for years, watching them evolve in real time. Sample returns may allow laboratory study of pristine material, yet none of this will eliminate the fundamental experience of a comet appearing in the sky. There will still be nights when people look up without instruments, see a pale arc of light, and feel a quiet sense of connection, not to a specific fact or prediction, but to motion itself, to the idea that something ancient has returned, briefly sharing space with Earth before moving on. In that sense, comets remain companions rather than subjects. They move through human awareness on their own schedules, indifferent to calendars and expectations. They remind observers that the universe is not static, but gently active, full of slow travelers following paths laid out long before anyone was there to watch. To live with comets is to accept that not everything repeats on human timescales, that not every visitor stays, and that some of the most meaningful experiences come not from permanence, but from passing presence. And when a comet finally fades from view, dissolving into faint dust, slipping beyond the reach of telescopes, it leaves behind something subtle but lasting, the memory of having shared a moment with deep time, written quietly across the sky. As our understanding of comets deepens, attention naturally turns forward, not only to the next bright visitor, but to the long, quiet future of these ancient objects. Comets will continue to exist long after current observers are gone, following paths shaped by gravity, time, and chance. Their future is not dramatic in a single sense, but expansive, unfolding slowly across eras far beyond human experience. In the near future, comets will continue to arrive from the distant reservoirs that surround the solar system. Subtle gravitational nudges will send new objects inward, just as they have for billions of years. Most will remain faint, noticed only by automated surveys and professional astronomers. A few will grow bright enough to catch public attention, briefly becoming part of shared human experience before fading again. Technological progress will change how these arrivals are detected and studied. Telescopes will find comets earlier and farther from the sun, allowing scientists to observe the earliest stages of activity. This will reveal how different ices respond to faint sunlight and how comets begin their transformation long before they become visible to the naked eye. Future space missions are likely to focus on endurance rather than speed. Instead of brief flybys, spacecraft may accompany comets for extended periods, watching them awaken, evolve, and fade across entire orbits. These long-term observations will provide a continuous record of change, capturing processes that currently must be inferred indirectly. Some missions may attempt deeper interaction. Concepts include drilling into comet nuclei, deploying networks of small instruments, or returning samples from beneath the surface. Such efforts would offer unprecedented insight into comet interiors, revealing layers untouched since the solar system's formation. At the same time, comets will play an increasing role in planetary defense planning. While the probability of a major comet impact remains low, understanding their structure and behavior is essential for preparedness. Future studies will refine models of how comets respond to applied forces, helping assess whether deflection is feasible if a dangerous object were ever identified. Beyond practical concerns, comets will continue to shape how humanity thinks about its place in the universe. As interstellar objects become more commonly detected, comets will be seen not only as solar system residents, but as part of a larger population of wandering bodies moving between stars. This perspective will blur the boundary between what belongs here and what comes from elsewhere. In the very long term, the solar system itself will change. Planetary orbits will shift subtly. The sun will slowly brighten as it ages. These changes will alter the environments comets move through. Some distant reservoirs may be depleted or reshaped. Others may release material more frequently as gravitational balances evolve. Eventually, far in the future, the sun will leave the main sequence and expand into a red giant. This transformation will profoundly affect the inner solar system. Many comets that survive until then will experience intense heating, dramatically increasing activity or destroying them outright. Others, far from the sun, may remain largely unaffected, continuing to drift in cold darkness. Even beyond the sun's lifetime, comet material will persist. Fragments ejected into interstellar space will wander the galaxy long after their star has changed. In this sense, comets may outlive the solar system itself, carrying its chemical signature into deep space. For human observers, however, the future of comets is less about distant astrophysical events and more about continuity. Each generation will have its own comets, objects that become reference points in memory. People will remember where they were when they first saw a particular comet, how it changed night by night, how long it lingered before fading. These experiences will continue to connect observers across time. Someone centuries from now may watch the return of a comet first seen in our era, linking their moment to ours through the shared act of looking up. In this way, comets serve as quiet threads, weaving together different moments in human history. They arrive without regard for borders or beliefs. They are seen by anyone willing to look. Their paths are impartial, their timing indifferent. Scientifically, comets will remain valuable because they are never fully exhausted as sources of information. Each new observation adds nuance. Each new comet differs slightly from those before it. Patterns become clearer, but variation persists. This balance between familiarity and surprise ensures that comet science will not become static. There will always be something new to learn. A different composition, an unusual orbit, an unexpected behavior. Culturally, comets will continue to hold a unique place. They are not constant like stars, nor repetitive like planetary cycles. They appear, linger, and leave. This rhythm resonates with human experience, mirroring themes of arrival, presence, and departure. As technology advances, it may become possible to predict comet appearances with increasing precision, yet the emotional impact of seeing one will likely remain unchanged. Knowing a comet is coming does not diminish the moment it appears. If anything, anticipation deepens attention. In the end, the future of comets is quiet rather than dramatic. They will continue their ancient routines, moving along paths shaped long ago, occasionally intersecting with human awareness. They will not announce themselves loudly. They will simply appear, as they always have. And when they do, they will remind observers of something enduring, that the universe is not built for haste. That meaningful change often unfolds slowly, and that even the most ancient travelers can still pass through our lives, briefly and gently, leaving behind a sense of perspective that lingers long after the light has faded from the sky.